What's up, folks? Welcome to this machine learning reading session with me. So today I'm going to go over this very famous paper for recommender system. Almost all the recommender systems that you encounter in the well-sized company are going to be use some similar architecture like this. So I read this paper a while back, but today we're going to go over it. So I'm going to just read each section and add my own commentary, so bear with me, and if you have any questions, you're welcome to post it in the comment section and we can have an interesting discussion. So wide and deep learning for recommender system, this is by Google. This is released 2016, but a lot of companies are still using it. Abstraction just usually in general talk about what the paper does. You can read through it to see if you're interested. So sometimes I skim through it, and if it's boring, then I'll skip it. So here it goes. Generalized linear model with nonlinear feature transformation are widely used for large-scale regression and classification problem with sparse input, like a recommender system problem. Memorization feature interaction through a wide set of cross-product feature transformation are effective and interpretable, while generalization requires more feature engineering effort. So later on it will cover, I hope it will cover what does memorization mean and what does generalization mean. So we'll see examples. With less feature engineering, deep neural network can generalize better to unseen feature combination through low dimension, dense embedding learned from sparse features. So if you recall linear regression, we have those features, but then we have those features, we literally have the handpick feature, like say for, if you want to predict if tomorrow is going to rain, right, you kind of guess the the humidity, all kinds of stuff, right, the temperature. But for deep learning, it's all kind of encoded in embedding, so that's why the comment. However, deep neural network with embedding can overgeneralize and recommend less relevant items when user-item interactions are sparse and high-ranked. In this paper, represent this wide and deep joint trained wide linear model with deep neural network to combine the benefit of both. We productionized and validated the system on Google Play. Okay, and you can explain what Google Play is. Online experiment results that this new model increased the acquisition compared to with only wide and only deep. So, introduction. A recommender system can be viewed as a search ranking system with while the input query is a set of user and contextual information instead of search term, and output is a ranked list. Given a query, the recommendation task is to find a relevant item and then rank the item based on certain objects, such as objectives such as clicks or purchase. So one challenge usually is similar to general search problem is to achieve both memorization and generalization. Memorization can be loosely defined as learning the frequent co-occurrence of items or features and exploring the correlation available in historical data. So my understanding of this is kind of basically have say 100 features, 100 different features for an item, and you kind of want to know based on historical data, if I watch A, B, C, would I also be interested in E, F, G, stuff like that. Generalization, on the other hand, is based on transitive or correlation and explores new feature combinations that has never been or really occurred in the past. So it's kind of abstract here. My understanding of this is wide is basically you handpick some features, and then deep is if I like A, B, and C, and then the obvious one that I would also like is E, F, G, but there's also H, I, J that's less obvious because those features, it's hard to handpick those features. but the model will still pick it up. I hope they gave an example because that would be a lot easier to understand. Recommendation based on memorization usually more topical and direct relevant, right? This is what I mean is by obvious, right? Compared memorization, generalization tend to improve the diversity of recommendation. In this paper, we focus on app recommendation for Google Play, but it can also be applied to other. For massive scale online recommendation and ranking system in industrial setting, generalized linear models such as logistic regression are widely used because they are simple, scalable, interpretable. The model are often trained on binary sparse features with one-hot encoding. Binary feature user installed equals Netflix has value 1 if user installed Netflix. So then conversion event here is installation. Memorization can achieve effectively using cross-product transformation over a sparse feature. For example, okay, so here it says user install Netflix and also user viewed Pandora. Pandora is the music app, whose value is 1 if the user install Netflix and then is later shown Pandora. So this explains how co-occurrence of a feature pair correlate to the target. Generalization can be added by using features that are less granular. For example, user installed video. Okay, that's why it's called generalization. So this is a good example. User installed video-related apps and then also view music-related apps. But manual feature engineering is often required. One limitation of cross-product transformation is that they do not generalize to query item feature pairs that have not appeared in a training set. Okay. Embedding-based models such as factorization machine or deep neural network can generalize to previously unseen query item feature pairs by learning a low-dimensional dense embedding vectors for each query. Okay, so for example, you pick 100 or 1,000 features, it's able to condense it to, let's say, a vector of size 100 and then kind of use in that vector space whether or not or whether or not an item and query are similar based on cosine similarity. However, it's difficult to learn effectively low-dimensional representation for query and items that were when the underlying query item matrix is sparse. Yeah, of course, right? Because the interaction is sparse. And high-ranked, such as user with specific preference or niche item with narrow appeal. Yeah, so it's not handling very well with those sparse cases. Okay. In such case, there should be no interaction between query item pair, but dense embedding will lead to non-zero predictions for all query item pairs and thus can overgeneralize and make it less relevant. Okay, that's a good point. On the other hand, linear model with cross-product feature transformation can memorize. Okay, so I'm just gonna highlight it here. On the other hand, can memorize these exception rules. Okay. So the example here is pretty good. I can also let me also highlight it here as well. So in this paper, we present a wide and deep learning framework to achieve both memorization, meaning what happened in the past, and then generalization, meaning the less obvious ones. By jointly train a linear model component and a neural network component in Figure 1, the main contribution of this includes, basically talks about the contribution of this paper. But yeah, here is basically the diagram that we should be looking at. So let's see. So you can see basically, yeah, wide model, that's just like very basic features going through, I'm assuming, activation function. And then you have some features that basically directly go into a sigmoid, but also kind of concatenate with, for example, this is like a deep neural network. You have embedding, and you have embedding like a bunch of vectors concatenated, right? And then they all have like their representation. And then you have hidden layer, basically just neural network, the MLP, multi-layer perceptron, and then you basically eventually combine them into one single vector, and then this all three you combine, that's your output unit. I think there's also another like sigmoid to combine them into like just one value for binary classification, or softmax to make them to a multi-class classification. So that's that. Okay, so here it still talks about just the general contribution. So the idea is simple, however, will show that improves the app acquisition rate on the mobile app while satisfying the training and serving speed. Okay, so it does talks about the engineering side, which is very nice because a lot of research paper do not cover that. So that's why this paper is kind of cool. So let's go over the recommender system overview here. 2. Recommender system overview. An overview of the app recommender system is shown in figure 2. So it's right here. A query which can include various users and contextual features is generated when a user visits the App Store. Okay? A query includes various users, contextual features. Okay, so like age, past history, what is the category of the page he's visiting, or all those kind of stuff, or location even. The recommender system returns a list of apps. Also refers to impressions. Impression here, I understand, it's just if user view it, it's impression. Otherwise, it's eligible or candidates on which user can perform certain actions such as click or purchase, and that is a conversion event. These user actions, along with the query and impression, are recorded in a log as the training data for learner. Learner, I don't know, I feel like it might be just like a servers that turn the log into some feature. Okay. Since there are over 1 million apps in the database, it's intractable to exhaust every single app within the latency, often 10 milliseconds, right? That sounds about right. Therefore, the first app upon retrieving a query is retrieval. Okay, that's a very typical like multi-stage recommender system. This is an interesting point because I'm always curious about what is the heuristics of these recommender system latency. So this could be a good rule of thumb if you're going for a machine learning engineer interview. So this is the retrieval step. The retrieval system returns a short list of items that best match the query using various signals, usually a combination of machine learned and human-defined rules. Okay. After retrieving a candidate pool, the ranking system ranked all the items by their scores. Okay. These scores are usually called P, Y given X. So the probability of user action Y, for example, purchase, given feature X, including user features such as country, language, demographic, contextual, such as device, hour of the day, of the week, location, even though you don't want to say it, and impression features like app age, historical statistics. So in this paper, we focus on ranking. So let's take a look at this. This is a very typical recommender system architecture design. You can use this for a lot of like recommender system interview. So it doesn't talk about the retrieval stage, but here, from my experience, it's basically something like an Elasticsearch with some sort of signal, machine learning signal in there to allow you to kind of narrow down. For example, you have a query and then it allows you to narrow down from all the items that you can recommend to maybe like, okay, here it says 100 items. Yeah, that's my experience as well. And then ranking, you further narrow down to 10. Yeah, so I like this heuristics. I mean, this paper is out 2016, so I feel like a lot of recommender system in the industry just kind of use this as a as a heuristic. Sometimes I think like 2030, but yeah, this is like a huge narrowing down. So that's that. So now it talks about the actual algorithm. Section 3, wide and deep learning. 3.1, the wide component. The wide component is a generalized linear model of the form y equals w, which is a vector. That's why it's in bold font. Transpose dot product x plus b bias. So mentioned earlier, x is the features, w is the weight you're learning, b is the bias. So this is a very typical, just kind of like a you can say neural network, or actually not neural network. This is just a very typical feature, kind of like a regression. Just you have a feature times your weights. Right? Y is the prediction, x is the vector of d features. D means like dimension, size of dimension. W is the model parameter, well, weights. The feature set include raw input features and transformed features. One of the most important transformation is the cross-product transformation, which you define as this. So this is what was mentioned earlier, where you do like cross-product transformation to get like basically crossing features. But in deep learning, you don't have to do that. In kind of traditional machine learning, you have to do that. So let's go over this. So this symbol, in case you forget, this is, so the other one that looks kind of like a E, that one is summation. This one is like a product. So for example, going from I to D, right? D here is the, say you have 10 features, then D will be 10. So for D features, I want, okay, so CKI. So let's read it. CKI is a Boolean variable that is 1 if the ith feature, okay, is part of the kth transformation, and 0 otherwise. So I think what this means is, so let's continue to read. For binary features, across product transformation could easily be an AND. Okay, so you're basically saying I'm going to not only use gender and language as a feature, but I'm also use naming combined as a feature, like an AND, using like a Boolean operation AND. 1 only if it constitutes female and English. This captures interaction between binary features and adds a nonlinearity. Okay, but this feels like a very hand-picked feature. So let's read this part again. So this is called cross-product transformation. Basically says, I'm going to basically, for K, okay, so what is K here then? Let's see. I'm assuming K here means like, okay, the kth transformation. So you're adding, besides like here you have like size D, like how many D numbers of features. You also add K numbers of this kind of like cross features. And what this does is basically says it's a Boolean variable that is 1 if it's part, okay. So let's just look at this. So I have this CKI, and then I say when it's 1, then it basically I multiply 2. But if it's 0, then I skip, right? For example, just say for example imagine I have just 2 features, right? So in a case where like I will have say x1, right, times x2 times x3, right? And this is the case where for example we defined CK1 as like if CKI is like 1, right, for everything. right? But sometimes, but it's not, you know, this is how, I don't know if it's learned or you define or handpicked it. Sometimes you don't pick this one, or or maybe you say for you know, my 3 features I want one, or so for, you know, for the first K I want all of them to be 1. For the second K I want like 1 to 1. Oh, so 1 0 1. So it could easily be like something like this. So it could easily be something like this. You could be like so when, or right, Ki is 1 for everything, right? So you have either like, so maybe that your when K equals 2, you G, right? So it's like, so it's likely, okay. So that's just my understanding. I have to look at the code, but this is basically I'm just handpicking and multiplying. But here you're saying and, but it's basically multiplying, right? Like, and they both have to be 1 to be 1. So that's that. So it basically, the y component is just your typical weight times feature plus a bunch of additional features that has this, you know, either handpicked or some sort of learning-based cross feature, okay? So the deep component, this is when you use neural network. So section 3.2. The deep component is a feed-forward neural network as shown in figure 1, okay? So figure 1 is right here, and then deep is here, okay? For categorical features, the original input are feature strings. Interesting. I thought they should be, okay, they should be encoded into one-time encoding, right? Each of the sparse high-dimensional categorical features are converted into low-dimensional and real-value vectors, often referred to as embedding. So, okay. Okay, so you have a string feature language equals, I think it should be one-high encoding direct lookup. That's my understanding. Okay, the dimensionality of embeddings are usually on the order of, okay, 10 to 100. Okay, that's pretty standard as well. I've seen 100, I've seen 10. Yeah, that's pretty standard. Embedding vectors are initialized randomly. So this is the part, yeah, I did not understand before, but I think a lot of people might be confused. Like, how do people get the embedding? Is it forward to back, or so what happens is they basically have sparse features like language, or for example here, like what language or location or gender, and they use like one-high encoding, and you have a direct lookup of embeddings for those features. And then what you do is the embedding vectors are initialized randomly, and then they are learned through training to minimize the final loss function. So the, you know, like the vector of size 10 or vector of size 100, right, is learned. These low dimension dense vectors are fed into high dimension. So I guess to clarify here, like it's sparse because it's one-hot encoding. That's my understanding. Let me just write it here. Yeah, I think that's what it is. So you basically have a one-hot encoding lead to a direct lookup of embedding. That's why it's low. So these low-dimensional dense, okay, low-dimensional means dense, of course. Low-dimensional dense embedding vectors are then fed into a hidden layer, basically like a multi-layer perceptron, and the forward paths. Specifically, each hidden layer okay? Each hidden layer performs the following. This is just multi-layer perceptron. You basically have I don't know if what A is here. Okay, L is the layer number, and F is the activation function, like ReLU. So in case you forget what ReLU look like, this is I can show you a picture of what ReLU look like. So So it basically looked like this, okay? So that's that. So after that, so here, right? You basically, so F is that. So you basically have A, B. I feel like this is like a multi-layer perceptron, and then result passing to a ReLU to kind of achieve that, whatever the non-linearity. So it's, it's more. So it learns something like more generalized. I think that's what it means. We'll have to look into it. Okay. Oh, I see. So B is like the bias. So this is similar, very similar to this thing. So B is the bias at layer 1. Say for example L equals 1, and A is kind of like the. Let's just go here. A is kind of like the features, I'm assuming, or whatever the. Not necessarily the feature, I guess it's the when you're embedding concatenated, right? It's like that is your, I guess, yeah, it's your feature vector, and then W is the weight, and then this is just like a multi-layer perceptron, and then you add a ReLU, and then that gives you the next layer. So you're basically saying, oh, my initial layer is this, next layer, next layer. So let me find a better picture. I think that I can hopefully find a good picture that explains the multi-layer perceptron. So let me find it here. Okay. Let me see if I can find it. So basically, I believe that one is this thing. If you look at it, multi-layer perceptron. Let's click into it. Right. Okay. Wikipedia has too many formulas. So what I want to show you guys is, yeah, it basically looks like this, right? You have your features, or here it's like you know x1 to xn could be like your vector, your embedding vector concatenated, and then each of them you basically, at this layer, A is, this is a really good picture, honestly. So this is one layer, okay? So A is the A here. So this is the weights. So you basically have all these weights, all these vectors times this weights, all these vectors times this weight, all these vectors times this way, and then they all go through, this. So in reality, it's like a vector, multiplication, and then it gets to here, and then you have a ReLU to kind of add the nonlinearity. So that's that. If I can find it, yeah, this is another good picture as well. So what all these does is basically, I have, all these features. I send them to the this weights, and then this outputs into this weight. So it's in this structure, okay? So it's pretty straightforward. When you actually code it, it's like you don't even think. You just have to figure out, okay, what dimension I want, and that's it. So how do you join the next section, how 3.3, join train of wide and deep model. The wide component and deep component combine using a weighted sum of their output logs. Okay. Components are combined using weighted sum, okay, of their predictions. So you basically let's look at this. Maybe I think there's basically a weight that you learn and you add them together. So we'll continue to read. Okay, here is a lot better. So yeah, that's figure 4. So we'll get to that figure, but which is then fed into a common logistic or log loss function for joint training. Note that there is a distinction between joint training and ensemble, actually pronounced ensemble. In ensemble, individual models are trained separately without knowing each other. That's true. So you're not optimizing towards each other. You're already trained separate without knowing each other, and their predictions are combined only at inference time. So this is a very important distinction. In contrast, joint train optimize all parameters simultaneously by taking both wide and deep parts as well as the weights for their sum into account at training time. So it's actually like it will optimize both during training time, or find optimization given the consideration of both wide and deep. There are implications on model size too for ensemble. Since training is disjoint, each individual model size usually needs to be larger. That is true to achieve a reasonable accuracy. In contrast, or saying, oh, our method is better for joint training of wide parts, only need to complete the weakness of the deep part with a small number of cross transformation rather than a full-size wide model. That's very interesting. So joint train of wide and deep model is done by okay, this is just typical like back propagation, typical machine learning stuff, gradient descent of both wide and deep simultaneously using mini batch, so stochastic optimization. So this is just the typical, if you read the gradient descent, just understand that's basically what it is. You're trying to find an optimization point using your kind of a derivative, or it's called gradient if you have multiple variables. In this experiment, we use the follow regularizer, so optimize algorithm. So just recall the regularizers to avoid overfitting, and then at a grad, this is their optimization function to find a gradient descent. So the combined model is illustrated in figure 1, but okay, that was one already show. So the logistic regression problem, so the model prediction is this, okay? So the probability of y equals 1 means user click given this feature is I have this sigmoid function, and then I have, this is the, what I mentioned earlier, right? How does it do the combine? Basically has another learned weights, and then for this learned weights, that basically it takes, okay, this is an abstract of learned weights. It takes in the feature we picked, it takes the cross feature, basically the dot, the x1 times x2, or those one that we pick, and each of them are vectors, and it also takes this deep weights that basically has the this multi-layer. So this multi-layer function. So this is like a very like abstract form. So, you look at this, you're not gonna understand. I think the best way is looking at this and this individually, and then just know, okay, that's how they combine. This is kind of already like a zoomed out view. Okay, well, y is the label, and this is the sigmoid as I mentioned, and this is I mentioned that of all. See, it says it's all weights, so this is like already the this is the very high level description, and then this vector weights deep are the weights applied on the final activation. Okay, so this one is referring to the one on the last, but I mean this is just like a high level to say how do we actually combine the final results. Okay, I see. So this is not even the how do I put it? This is not even the formula for the full model, right? This is, the left part, this is obvious, right? This is the basically this with this. The right part is not even this. This is more like kind of like a recursive form where you have layer 1, layer 2, layer 3, all the way to layer final. And then when you have layer final, and then you have a value, and that's when, you know, this is for. So this formula only say, oh, I'll give me the final layer of your activation function, and I'll give you, you know, this is how we combine this with the white portion, which is just the basic linear function. Okay. So this is the model part. I hope it gets a little bit more clear. So model training. Okay, so I want to go over figure 4, but it will be covered here. So let's just wait until we get there. System implementation, section 4. The implementation of app recommendation pipeline consists of 3-stage data generation, model training, and model serving as shown in figure 3. Okay, this part. So again, this diagram is always nice for, you know, system design interviews. But this is pretty straightforward. You have user data. I'm assuming just like user features, user profile data, and then impression data is like user interaction events, and then training data generation, probably some sort of join. I'm sure there are some like fancy like details like how they will sample because they can take all the events. I'm not sure what this one is. And then they send to the training, probably had to compare with the previous model to decide if they want to promote or not. And then if they decide to promote, maybe there's this another, maybe this is what, you know, to decide whether or not to promote this new model or not. And then the model server, and then maybe this is just the backend that's connected to, you know, very close to that front end side. So that's the architecture. It's pretty neat. Let's see if it explains what the vocabulary generator is. Okay. So data generation, in this stage, user and app impression data within a period of time are used to generate training data, of course. Each example corresponding to one impression. Well, sometimes you have to dedupe, but that's a whole different story. Label is app acquisition, so that means if the user download that app, then it's a positive event. If the impression impressed, okay, acquisition means if it's downloaded, yeah, installed it, and then 0 otherwise. Vocabulary, which are table mapping categorical feature strings to integer IDs. Okay. See? So they do have this vocabulary generator to map all these, what's it called, categorical features? Yeah, feature strings into individual IDs, right? Because recall earlier in this diagram, right, you need this like sparse feature, which is basically one-hot encoding, right? That's what that vocabulary mapping thing is. So you know, okay, for ID 2, it's mapped to like this embedding. So that's what that means. Okay, so are also generated in this stage. Okay. The system computes the ID space for all stream feature that occur, okay, more than minimum number of time, okay. So this means that the feature is not just like you know, demographics, that kind of stuff. Maybe there are some other stream features they're taking into consideration. We'll see potentially in the diagram figure 4. Continuous real-time values are normalized to 0 to 1, of course, otherwise you will skew your prediction. By mapping the feature value to its cumulative distributive function p divided into in quantile, okay. This is some stat stuff, you know, but we just need to know it's normalized 0 to 1, and there are different ways to, this is what they choose to, okay. The normalized value is, okay, so this is how they use this NQ, the quantile for value for the ith quantile. Okay, quantile boundaries are computed during data generation. So it's normalized not by divided by average, not by divided by max, but they're using this kind of like divided by the quantile, but you know, it will be guaranteed to be within 0 and 1. So I think it basically continuous features. I think what it does is basically saying I have a bunch of numbers and let me sort them in descending order, and then if this yeah, okay, so if this number is like, say if I have 100 number from 100 to 1, then one of this feature, real-time feature, is 99, or sorry, if 98, then it will be 0.98. So it's mapped to the quantile is basically like you sorted the value and then you divide them by sections. So if we have 100 values, 100 distinct values, then we have 100, and then we still want 100 quantiles, then each one is their own quantile. So 89 or 98 will map to 0.89. So that's my understanding of this quantile boundary method. But in reality, you might have 100 quantile and then you might have 100,000 values. So then you need to figure out, okay, how do you, what's the it's called the cumulative distribution function. But yeah, basically that's what it is. You do the descent, you basically sort them in descending order, and then you say, okay, what are the numbers, how many of these numbers add up to the top 10%, then that's your first quantile. So basically like that, you can look into it. So the next step, 4.2 model training. Now we finally get to talk about this figure that we saw earlier that we want to get to, okay? The model structure we used in the experiment is shown in figure 4. During training, our input layer takes in training data and vocabulary and generates sparse and dense features together with a label, okay? So it basically, a label, basically you have a label like yes or no, the user done or not, and map to a list of features. That's your one row, right, of training data. And then the white component consists of the cross product transformation, of course, of user install app and impression apps, okay? Okay, so they're basically saying for that, they basically just have user install apps, and maybe it's a little bit more complicated, but basically user install the apps and impression apps, they basically cross those two and say that they're creating another feature. So that answers our previous question, the cross product transformation, or how they kind of combine, say I want feature 1 times feature 2 as a new feature, it's handpicked. So that's what explained here. So for the D part, a 32-dimension embedding vector is learned for each categorical features, right? We concatenate all the embeddings together. That's why you put them like this. They concatenate together into this giant dimension, 1200. Not so giant nowadays with a large language model, but for this type of model, it is pretty big. The concatenate vector is then fed into 3 ReLU layers. So these are the ones that we talk about. There are 3 layers. There are 3 layers, and so there are 3 layers. So let's just revisit what ReLU look like. Okay. Okay. So ReLU look like this. Okay. Right. Basically, 0, 0, 0. So if less than 0, 0 is greater than 0, then it's sort of a linear, function. So it basically says. So for example, I have this, 1200 size of 1200 vectors. I path them through a multi-layer or like a perceptron, and then I want to say my output is 1024, but then I also want to pass them through a ReLU. So if it's less than 0, they become 0 greater than 0. They keep their own value, and then another one similar, but the size slowly reduce, right? So that's what this does. So that's what that is. I want to show you guys a single perceptron. I think that's a little bit easier to see. Because this is what a single layer, like a single perceptron look like. Basically, imagine, right, I think this is a pretty good picture. Imagine I have like 1200 dimensions, right? For a single one, I basically say I want to, for each of them, I want to time this wave vector, and then I'll give them a wave vector, and that way, and then I sum them, so that's one value. But then if you do like a, when it's multi-layer, it basically becomes you have a vector. You have a vector, right? So you have So you have 1200, and then you have basically you multiply some time of a weight vector, and that is able to shrink it to 1024. So it's all like linear algebra, I believe. And then after that, so for that 1024, you want each of them to go through a ReLU, basically saying if it's less than 0, I want it to be 0, greater than 0, and to be 1, I'll be, if it's the same value that comes in. So that's that, right? So 3 layers, and then I want to see what this line means. So we'll see if it explains it. The YND model is a trained on over 500 billion examples. That's a lot, okay. Every time a new set of training data arrives, the model needs to retrain. Wow. So that's a lot. However, retraining from each time is very expensive. That's what I'm thinking. To tackle this, we implement a warm start system which initializes a new model with embedding and linear model weights. Okay, so this is sort of like a transfer learning, or we call the pretrain nowadays in all these transformer world. Right, we basically take the previous weight and say, oh, let's start there. Yep. Before loading the model into a model server, a dry run is done to make sure that it is not causing problem. Okay, so that's what this one model verifier is for, I guess. Before it sends to the server, it basically, serve some live traffic to see, or simulate some live traffic to see it will not blow up. Maybe there's some sanity check there. Okay. I see. Okay, remember our earlier question that what does this mean? So this is basically saying I want user install app and impression app. I want those two kind of features. Basically, those categorical features to be basically a dot product. So something like that. Basically, if user install app 1 and the user also install impress app 1, then it will be 1.1, or it will be 1.0.1 if it's a user install one app, I view the other app. So it's something like that. Okay, I see. That makes sense. So experiment. So here is talking about experiment. We conclude live online experiment in an A/B test. Okay, and for 3 weeks. Okay, that's pretty good. We have a control group. 1% of users random selected and presented with recommender or previous version. Okay. So the control is using the previous version. I understand experiment is actually very important. Like a lot of machine learning books don't talk about experiment, but like if you want to be an MLE, a lot of these like how to set up experiment is actually very, very important. Which is highly optimized. Okay, wide only. Okay, regression model with rich. Okay, with rich cross product transformation. So here what it's saying, the previous version is not. It's basically saying before this model is even launched, they're basically have the control group as the previous version. Basically, it's not even a deep learning model. Okay. For the experiment group, 1% user were presented with the generated by YND model trained with the same feature shown in table 1. So they basically they have Google has enough traffic that they can just take 1% for experiment, 1% for the control. Okay. So shown in this table, so control is the super wide one, offline UC is this, and then this is just with the deep is this, and it's higher. Okay, it doesn't look that much higher offline, honestly, right? It's like not even 1%, but okay. Okay, so, but maybe it's a lot because let me do a quick math here, right? So if you have 0.002 divided by 0.722, okay, and what does that get you? That's less than Okay. That is not a lot. That's crazy. That's not even, to be honest, that's not even 1% improvement from here to here. But look at how much acquisition gain online it gets. That is crazy. That's kind of like, this is like a real life example of don't rely too much on online AUC, because you actually like offline results have a small improvement. Your online result, I mean, this is measured obviously by a different metric, can go up by a lot. Wow. Results will also compare with another group using, right, so this is compared with the deep, right, +1. Okay, that's what it's trying to say. Based on online experiment, okay, AUC on the holdout, okay. Besides the online experiment, so this is talking about, okay, the offline experiment, okay. Right, while when deep has higher online AUC, the impact is more significant. Yeah, no, yeah, that's, yep. Let's see what they explain. Is that the impression labels in the offline labels are fixed. The online are generated with new Explorer. Okay, exploratory, okay, recommendation by blending generalization. Learn from new users' response. So what it's saying, I mean, I think people in this field might encounter as well, is like the offline don't go up by that much because you know you have a fixed data set. Maybe in that data set it can't go up by that much, or there's some innate noises. But online, you know, the money making, this is the real one, right? Serving performance. So okay, with a single thread. Okay, this is, they briefly talk about it, but this is not the focus of this paper. Okay, so related work. Okay, usually we skip the related work. Conclusion, but conclusion is memorization and generalization are both important for recommender system, right? While linear models can memorize, wide linear models can effectively memorize sparse features. Right, the wide linear, which is something like this one, right? The wide can memorize. Wide linear model can in fact memorize feature interactions using cross-product features transformation, but the deep can generalize better. So we present this wide and deep, and then they also explain how the production is. So this is actually a pretty good paper. I think what happens, a lot of recommender system in production nowadays in startups are using this this model. So I'm glad I finally get to go through this reading session with you guys. So thank you for watching. Thanks for your time. And in the future, I might do a hands-on session on this. If you like this kind of format of going over some of these famous papers in recommender system, in search, or in ads, or in, you know, some of the state-of-the-art machine learning technology, let me know. I hope you guys enjoy it. Hope this is helpful. Thank you.